Hey guys, I'm going to show you how to prove that two triangles in this figure. So I have a tangent and a secant segment. I'm going to show you how to find two similar triangles here. First, I'm going to start by just drawing two more chords. And in order to show you that there's a couple ways to look at the two triangles, but I'm going to show you that ACD is similar to DBC, which is also kind of like right in there. DBC. And I can start by just saying that angle C is congruent to itself. I only need to find one more angle that's congruent. So if I were to start my proof, I'd say angle C is congruent to angle C. That's the reflective property. Okay, well, what else do I know? There's some inscribed angles in this circle. We know some things about inscribed angles. First, we know that angle A, its measure, is 1/2 of the arc it intersects. Well, it intersects arc BD. Where's another inscribed angle? Well, there's an angle right here, and angle B is 1/2 of arc AD. So okay, measure of angle. Actually, I should probably label this one. ABD is 1/2 the measure of AD. Okay. And I think there's actually one other inscribed angle, and this is one that if you miss this one, this proof would be really hard, but if you know it, it's really easy. This angle right here is technically an inscribed angle. So an angle that's formed by a tangent and a chord. The angle between the tangent and the chord is going to be 1/2 of the arc that's intersecting it. Here's the arc. It goes all the way along here. So this angle is 1/2 of this arc. Remember, that arc would be defined by the central angle out here. So back in our figure, angle BDC, measure of angle BDC, is equal to 1/2 the measure of the arc it intersects, which is BD. Okay. So if you take just a second, you'd notice that, well, we have two angles then that are going to be equal, right? I have this angle, angle A, which is over here, and angle A is that we know it's equal to angle BDC, which is in this triangle, BDC. Well, that's enough for me to prove these two triangles are similar. In my proof, though, I'd just take it one more step at a time. I'm going to say measure of angle A is equal to the measure of angle BDC. And then because they're equal, I'll say they're congruent. Angle A is congruent to angle BDC. And then because these two angles are congruent and these two angles are congruent, I have enough to say these triangles are similar. So I'm going to say triangle. And remember that the order of the points you name matters. So I'm going to go A, C, D, which is kind of alphabetical, is similar to triangle. Okay, then in this triangle, I started up here with my double slashed angle. So I'm going to start down here with my double slashed angle, D, and then I went to the single slash, so DCB. DCB. Cool. Okay. Because those two triangles are similar, I can form a proportion. I could say that AC over CD, right, AC over CD is equal to DC over CB. One thing to notice is that DC is the same as CD. It just looks a little bit nicer if you say it the same way here as you've already said it here. And then from this proportion, if I cross multiply, I could write a new relationship that says AC times BC, okay, because I changed CB to be BC, just to make it look a little nicer, equals CD times CD. I'm going to just write that as CD squared. So those are the statements that I would make in proving that this is true, given a tangent and a secant segment. I imagine you could fill in the reasons, right? All of these reasons here, where I have half of an arc, would be just the properties of an inscribed angle. So you could say inscribed angles are half of the intercepted arc. This is substitution. This is the definition of congruence. Angle-angle similarity. This is, you could just say like similar triangle proportionality. And all we did here was we cross-multiplied from above, so you can call this just multiplication. That's the reason for that step. That's how I do that proof.